Well, hello and welcome to our next 3D and 30 session. Today we're talking about metal 3D printing and how it is accelerating the testing of hypersonics at Zucrow Labs. Often we work with companies looking to provide solutions for supersonic and hypersonic technologies, but strangely enough, they're not willing to talk about their parts publicly in a LinkedIn Live session. Luckily, we're also working with a team of experts from Zucrow Labs at Purdue. And we're joined today by Professor Carson Slabaugh and test engineer Nick Strahan and our own Gene Miller to help us learn a little bit more about how 3D printing is driving the research of hypersonic vehicles forward. Today, we're going to be talking about the extreme environments that hypersonic crafts experience and the links that engineers must now go to in order to recreate them. So I'm going to open the panel and just give us a little bit of a background about yourself. Carson, if you could just kick this off, please.
Sure. Yeah, my name is Carson Slaybaugh. I'm an aerospace engineer, and I'm a professor here at Purdue. And I do all my research at Zucrow Labs. So we've been working out here as a group for about 6 years. My team has about 20 people in it. And we focus on a wide range of different problems, from rocket engines to hypersonic combustion systems, and our goal is to make these propulsion systems perform more efficiently and go faster.
Nick, a little bit about your background, please.
Sure. So I'm also an aerospace engineer and a PhD student working for Carson. So I focus on working on hypersonic testing contracts. And right now I'm focusing on this design for a wind tunnel, which we'll talk about a little bit later. So that's about me.
All right, Gene, I'll let you wrap it up.
Yeah, hi, I'm Gene Miller. I've been with VELO3D about 5 years now, started as a process engineer. My background's primarily in conventional manufacturing, machining, casting especially. So a lot of these, legacy manufacturing techniques, I get to help leverage into why metal 3D printing is so valuable. So really excited to be here and to talk about the advantages for metal 3D printing, particular VELO3D's unique take on metal 3D printing, and how we helped Zucrow get to where they want to be.
And since you said metal 3D printing, I think we'll kind of go around. Carson, what was your first experience with metal 3D printing?
Well, the first time I worked with a additively manufactured part was actually a injector for a gas turbine engine. One of the major advantages that we were excited about there was reduction in weight, and because we could get rid of joining surfaces and very complex geometries, and also being able to come up with better mixing geometries and things like that in a gas turbine. So this is my second time printing a part that goes into a combustor, and it worked great last time, and so we decided to use some of the same ideas here moving forward for creating a hypersonic environment to test our combustors in.
And how long ago would you say between those two experiences?
It was about 3 years ago or so when we first started working on that other injector.
Have you seen the technology change in that time, or what stood out to you?
One of the things that was, I think, most important to us here is the density of the material, with minimal heat treatment or other effects that we had to do afterwards. Being able to pull something actually basically out of the printer, do a little bit of cleanup machining, and then drop it right into our combustor. That's a significant improvement from what we were able to use even just a couple of years ago.
Nick, what was your first experience with a metal 3D printed part?
So actually, this project was the first design experience I had, and it was really great. Honestly, we had essentially approached this problem with subtractive techniques in mind before you came to us, and really there were a couple of design features that were going to hinder the performance of this combustor, and doing it additively made us able to integrate this swirl of geometry into our combustor much more easily. And kind of some of the unique features about this flame would have made that impossible otherwise. So yeah, it was a really great experience, and the technology made a lot of things possible that we simply couldn't have done other ways. So.
You mentioned kind of features that wouldn't have been possible. Are you able to expand on that, or is this some of this?
Sure. No. Yeah, absolutely. If you have a picture of the swirler, you can see it pretty well. But we have a fuel injection at the center, and it basically has to be suspended in the middle of our oxidizer jet. And we have these swirl vanes that direct the oxidizer in a way that allows us to achieve really good mixing. And that basically that post in the center of the swirler has to be suspended, and doing it subtractively wasn't really possible. We weren't able to get something like a wire cut process into the really small orifice of this injector. So again, something that the additive manufacturing techniques really enabled us to do, we wouldn't have been able to do otherwise. So that was great.
Gene, you have a little bit of background, and Nick was kind of mentioning the challenges with trying to cast something like this. What color would you have from your experience?
So if you tried to cast something like this, you could do like a lost wax or an investment mold, something like that. But then again, you're paying for tooling. You have a longer lead time. Depending on how thin and the process that you're using, you might have challenges with cold shuts on some of the fins because they're pretty thin. And it's kind of a guess and check with casting. You design the tooling, you pour a mold, you see what problems you have, and then you iterate again and again and again until you get a good part. So really, I think in this case, the lead time just blows traditional casting right out of the water.
And you kind of mentioned iterations, and I know we showed a picture with 4 different pieces. Are those all different, or are they the same?
Well, I mean, maybe Nick or Carson can elaborate here, but the very changed on the blades themselves, and for each test they could do a different geometry. And again, you don't have to design different tooling here, so there's just no comparison with trying to produce a cast part, especially in different versions like this.
Okay. And Nick, what was your strategy around doing the different parts, or Carson?
Yeah, I mean, the parametric variation that Gene kind of alluded to was really critical for us here. We were able to change, got one on my desk here, but yeah, the vane angle that you can kind of see in the photos, we were able to tweak that to a pretty fine degree, by just, and it was, essentially a click of a button, right? We sent a step file, and, we had just a small change in geometry, and you guys were able to print them for us, which is really valuable for us. Doing this subtractively or through a casting process, as you noted, would have been much more expensive for tooling, especially doing 4 different versions, because these were not parameters that we could have changed otherwise. So,
and I'll just add to that quickly. These are very complex flows. We're creating, intentionally designing turbulent flow fields so that when we inject fuel, it mixes at a certain rate, and we can actually stabilize a very powerful flame in a very compact volume. And the way you do that is, it's a very complex process that's often done iteratively, because we don't actually have, even with massive supercomputers, the capability to actually predict what these flames are going to look like in the design process. And so it's key to be able to actually rapidly test and evaluate. And that helps us, reach an optimal design much more quickly. So this is enabling in that sense.
And I know we've kind of dove into this specific part. Maybe we should back up a little bit and provide everyone a little, the context with what exactly you are trying to create here. So maybe
Sure.
Carson, if you could take a shot at that.
Sure. Yeah, I can jump in on this. What we're interested in doing, working in the space of hypersonics, is recreating in a laboratory setting the environment that a hypersonic vehicle is going to fly in. For us to be able to test propulsion systems, combustors, things like this that are going to operate when we drop them out of the weapons bay of an F-35 or something, we need to know that these systems are going to work on the ground. So this combustor that we've developed is allowing us to do that. When a vehicle flies through the atmosphere at 6 times the speed of sound, it's effectively flying through a fireball. The temperature of the gases on the surface of that vehicle can be 3,000 degrees Fahrenheit. The pressure's in excess of 700 psi, maybe more than that. So depending on what altitude you're flying at. So these are very hot, very high pressure flows, and the vehicle has to, one, withstand that kind of tremendous heat load on the external body of the vehicle, but then also, in the propulsion systems we're looking at, we're taking in air from that environment and then injecting fuel and burning it, and still trying to generate thrust too. So, as I mentioned, it's quite literally a fireball that the vehicle is flying through, and so we're using a flame on the ground, a very powerful one, to recreate that in our lab, so we can study these processes further.
Is that what we're seeing right now in the image here? Maybe you could talk us through what we're seeing.
Sure. Yeah. These tests that we just wrapped up, and what you're seeing a video of right now, is a single element version of the laboratory scale combustor that we're going to be that we're building in our lab. So we're building a very large burner. It's effectively a large rocket engine that we're going to be putting these test articles into the plume of, and so we wanted to see the film structure, understand its performance, before we build the larger scale system. And so those tests are that's what we just finished up running. That's what that video was of. Maybe the high speed video might show a little bit more detail of the flame structure and the sort of things we were looking at.
Interesting. And I do want to remind everyone, we're doing this live on LinkedIn. Please feel free to submit your questions at any time, just in the chat, or give us an emoji, a thumbs up, let us know how we're doing. I'll love to interact with everyone whenever we can. Great opportunity to get your questions out on things that are publicly accessible for Hypersonics. So I guess kind of in that vein, what got you interested in Hypersonics?
Well, I mean, I'll go first. I've always just been interested in, very high performance aerospace systems, and this field of hypersonics is really just the bleeding edge of our technology right now. How fast can we propel these vehicles or these projectiles, regardless of what the application is. Being able to launch a system and get it up to these sorts of extreme speeds is a real technological challenge and feat to be able to do it. So it's a fun place to work.
And we did mention
from the bottom there, and the flow going in from left to right. So.
And I think maybe the audio just got cut off when the video came in. Could you just say again what you were saying when that video was up?
Oh, yeah, sorry about that. Yeah, we're trying to examine the structure of the flame. That tells us a lot about how it's performing, what its efficiency is like, what sort of susceptibility it has to instabilities and things like that. So you could kind of see that complex turbulent flow. Any of the lighter colored regions in that video were actually flames, and the way that's interacting with the turbulent swirling flow coming out of those injector vanes is what we were able to see there.
And Nick, same question to you, and then we do have something from the audience that I want to dive into. But what got you interested in hypersonics, Nick?
Can you guys hear me? Okay, there we go. Yeah, so I basically joined the group before I think I really knew I wanted to be involved in hypersonics. But I worked on a testing contract for a company that was kind of designing a combined cycle turbine ramjet engine. So it was kind of, again, the bleeding edge of what's becoming really popular now these days, companies who are working on commercializing hypersonic flight. And I thought that was really fascinating. So just kind of the, like you noted, hypersonics are becoming more and more publicly available and publicly accessible, and I thought that was really cool. So I had to be a part of it.
You make it sound like, chess club, hypersonics. It's Thursday night, so it's hypersonics night. I'm sure there's more.
It's a fascinating engineering challenge for sure.
So we do have a question from the audience. What kind of software are you using to design the parts, or maybe even to simulate the performance of them?
Sure. We use a variety of engineering design tools when we're designing combustors like this. It can be anything from CFD packages like ANSYS to structural analysis packages, also ANSYS, or other finite element tools. CAD. A lot of our design codes are written in MATLAB and Python, but I wouldn't say there's one particular tool that we use. We really have to pull together engineering knowledge and kind of use different softwares in different ways to attack different parts of the problem. It's a engineering system, not necessarily a single problem. So it takes a lot of effort and using a lot of different tools.
And like, I know we kind of did some of these requirements of the application. What type of metal was used for this?
These were Hastelloy X. So it's basically a super alloy that's designed to operate at very high temperatures, similar to stainless steel is the more commonly known corrosion resistant alloy, and this alloy is similar, except it can go to much higher temperatures and withstand the environment that we were subjecting it to inside the combustor.
And that's kind of what drove that decision, was the environment that it's in.
Yeah, exactly. The injector does have some very precise geometry, and we need that geometry to stay as we designed it when the combustor is firing. So Hastelloy X is one of the few materials out there that can handle that environment, and it's very common in gas turbine engines. Things like Inconel and Hastelloy, basically nickel-based alloys that are again able to take these really high temperatures.
Do you see any? There was a question on this. They actually came in right
Sure.
when we were addressing that. Is there what do you see as the future of materials? Where do you think this could go going forward? Do you have any background there?
I would actually probably direct that to Gene. I think you probably have a better handle on the materials than me, but.
Well, I mean, there's a whole sea of materials out there that are currently under development as far as even just chemical composition. And then there's even this further development of applying it to the process, the laser powder bed fusion system. Is it weldable? Is it something that we can use? And for really, really high temperature applications, we're looking at things like, and this might be outside of the realm of hypersonics, but for rockets, we're looking at copper alloys that can really conduct heat very well and still withstand these high temperatures. We're looking at niobium alloys that can withstand extremely high temperatures. And yes, there's a lot of opportunity there in those type of alloys. But to know exactly where, that's difficult to say. There's a lot of development in a lot of different avenues. But I'm hearing a lot of buzz about copper and niobium.
There was a question here also regarding the softwares. Do you use any topological optimization software?
So we haven't. I think I have a bit of experience with that kind of software from a previous role where I did more structural work. But in our application, we're really taking the topology or the geometry as the input. So we don't necessarily have a good way to optimize topology because we're not looking at a set of known load conditions or boundary conditions and then trying to figure out an optimal geometry. It's more like we know the geometry and we want to verify the shape of the flame that the geometry produces. That's kind of the approach that we take in this type of design. So it's almost an inverse problem to a topology optimization, if that makes sense.
And you kind of mentioned testing these out. Out of the ones that you designed, was there one that outperformed? And if so, what were you looking at to make that decision?
Yeah, so we have one design that we think is the winner so far. We're still looking through the data. We wrapped up testing, I believe, the beginning of last week or the end of the week before that. So there are a lot of different things we need to look at. Probably the most important is flame shape we talked about. So in the high-speed imaging that we took, we're really trying to verify that the flame achieves really good mixing in the combustor and doesn't produce a very long flame that has poor mixing characteristics. Again, the goal of this device is to generate a flow that simulates an atmosphere at very high flight speed. So we want it to be as uniform as possible. So that's like our number one design goal. Secondary goals were things like stability. So again, this is going to go in a device that produces flow for other test articles. So we want this device to be really reliable and very stable for all operating conditions. So we were looking for things like thermoacoustic instabilities in the experiment. And of course, we would design to avoid those when we go to our full scale version. So yeah, there were a number of different parameters, but we're kind of, I would say, between 3 and 4 different key parameters, we're trying to find a good compromise with the 4 designs we tried.
And you kind of mentioned the mixing, and I know, Gene, you mentioned the different pitch of the blades, I guess, for lack of a better term. So varying that seemed to be important in this process. Would that be fair to say?
Yeah, for sure. So we varied two distinct parameters. We two sets of the swirlers had a 1 vane angle, and then the other set had a different size for the oxidizer orifice. So basically the hole you're looking at in the back, that size changed for 2 of them. And yeah, so we're varying what we call the swirl number, which is a metric that kind of describes how fast the flow is turning in the axial direction, or turning about the axial direction, I should say. And that kind of directly relates to how well the combustion gases mix. So that was really what we were varying, parametrically, I guess you could say. So we're looking at that as the driver for those outputs that I told you we're trying to optimize. So.
And Gene, this one might be more kind of for you. There was a question: how does VELO3D reduce the prototype development time for an opportunity?
So, I think the biggest savings and biggest advantage here is making the step from traditional casting or legacy manufacturing into metal additive manufacturing in general. How Velo helps push that a little bit beyond in this part, which admittedly might not be the greatest candidate to see the benefit for VELO3D. However, we have the unique ability to build really delicate support structures. And like Nick was mentioning before, those vanes where they initiate are tucked inside the part. So what we did was actually make some very delicate, very high aspect ratio supports to just touch those vanes as they initiate. And those were able to be just removed by a simple pair of pliers and some tugging and fatiguing it off. So it eliminated some post-machining or some really complex processes in order to remove those supports on the vanes, which the vanes are the integral part of this part. So it gave us a unique opportunity to do that.
Okay. Was there any fatigue or other type of nonlinear structural analysis? And if so, what would you use for that from a solution point of view?
So for this application, we didn't do any sort of fatigue type analyses. Typically for our application, since we're looking at research hardware, the lifetimes are very, very short. This test article may be around for a long time, or this hardware may be around for a long time, but we don't test it at a very high frequency. So we tend to make sure they're very well designed structurally, and we have high factors of safety. But we design them with a low enough duty cycle that fatigue generally doesn't play into our design process. Not to say that it isn't important, but it's just that our duty cycle is so unique, being that we're a research lab, and we test infrequently compared to a real engine. It doesn't usually cross our design space.
I'll just add to that one of the key parameters that Nick mentioned we were testing to optimize these burners is combustion instabilities, which can be a source of very rapid loading of the part at very high cycling rates. So fortunately, our designs have proven to be pretty insusceptible to that. So again, our fatigue concerns are kind of taken away even in the design process. Had we seen those issues, we would have made adjustments to make them go away.
Okay, and it is like you mentioned that you were analyzing the data. What are the next steps in this program?
Yeah, from here, we're going to take the design that produced the most robust and efficient flame, and that will be the foundation for this large-scale air heating system that we'll be building next. So we've been testing with a single element. The big burner will have 7 of these elements actually, in an array, and that will feed into a large scale. It's basically a rocket combustor. It looks just like a rocket combustor with a converging diverging nozzle at the exit, and that creates the conditions for all the things that we're going to test downstream. So we hope to have this whole system running in the early fall timeframe, August, September, and we'll be we'll be on to testing hypersonics after that.
So do you get mock diamonds, or is it so contained you don't get them?
No, yeah,
No, we do.
shockwaves everywhere. Yeah, for sure.
We need some pictures of that. That's what's up there. Cool. And just a reminder, we are taking questions live. So if you want to learn anything more about what the team at Zucrow Labs is up to with regarding hypersonic testing, please send in your questions. So we did mention one thing kind of in rehearsal. I think I talked about it in the beginning, that we deal with companies with supersonic and hypersonic, and I do think it's probably an interesting conversation, at least for me it was, to know the difference there, and how do you think about those two realms?
Yeah, so the classical delineation between supersonic flow and hypersonic flow is at Mach 5. If it's between Mach 1 and Mach 5, it's supersonic, and if it's above that, it's hypersonic. There's for us as propulsion people, really one of the major differences is a change in engine architecture that happens around that Mach 5 number. What we're really interested in looking at with this setup are a combustion or a propulsion device called Scramjet. That stands for a supersonic combustion ramjet. At hypersonic speeds, you simply can't slow the flow that you're pulling from the atmosphere down enough to combust it at a subsonic speed, and so you have to burn your fuel with air flowing through your combustor at Mach numbers of 2 or greater, and so it totally changes the entire engine architecture right around that speed. So that's kind of the way we see the difference.
That's interesting. That sounds like a lot of technology we can't talk about.
Yeah. Well, that's just we can stop there, but
yeah. And so there are craft like the space shuttle. I remember that would be hypersonic, right?
Yeah. When the space shuttle, I guess the shuttle's an interesting, or any orbital rocket like that is an interesting problem, because they start off at Mach number 0 when they leave the ground, and they go through a Mach number transition at Mach 1, and then certainly when they're coming back and re-entering, that's definitely a hypersonic flight regime with very high Mach numbers.
Yeah, definitely never been through that. A couple more questions coming from the audience, and then I think we're getting close to the 30-minute mark. So the question is, do you only use AM for prototypes, or are you going to also use it for production? Which I guess in this case might be very similar things.
Definitely, additive manufacturing is also used in production, and a lot of these high-speed systems like this. It's an enabling technology for many injector design approaches or thermal management approaches and things like this. So most of what we're doing is prototype testing or research and development in our lab setting, but it's because it's going to go straight to the vehicle once we find the optimal solution. So.
Okay. And then last one is regarding the 3D combustion modeling for your flows. Do you find that reliable, or do you mostly rely on cold CFD in experiments?
Most of maybe a little bit of a joke, but we most of our work is actually proving CFD wrong and helping people improve those models. It's a really combustion is fundamentally coupled between the flow physics and the chemistry, and at these highly turbulent flow conditions, it can't all be resolved in a simulation. You always have to rely on some sort of simplified model in order to make the computations affordable. Even with exascale type machines, you still can't directly simulate all the physics that are occurring in a flame like this. So yeah, it's model validation and development is really what a lot of our experimental data gets used for.
And I know I said we wouldn't take one more, but I really like this next one. I think it's a great way to summarize it. Where would you like to see more development in this field? Materials, hardware, design, simulation?
I guess I can jump in and answer that. Definitely in the a lot of complex systems and high-speed air breathing propulsion have heterogeneous material architectures and things with coatings applied to superalloy materials that are joined to other materials. It's a really cool area to think about how additive might be able to really impact the way we think about design of those parts and joining them and assembling and things like that. That ended up being a major factor in my first experience with additive manufacturing, and certainly seems like in the high-speed area it's going to be a major strength to play on.
And we'll just use this as our closing question, so we'll go around the horn with it. Nick, what are your thoughts? Where would you like to see more development?
I'd have to agree there a lot. Just with this experience and seeing how flexible additive is to prototyping things like this for a research context where we are often flipping through prototypes quickly or trying different things, additive is really helpful. And I mean, this part, we couldn't tell the difference between this and a machine part in many ways. So the technology is there. 10 years ago, it seemed like a fantasy, but we were really getting parts that are just as good as machine parts at this point. So it's pretty amazing.
Gene, we'll let you close it out.
Okay. I think, first and foremost, materials are very important to, expand the design space or the application space for AM and the capabilities of that component, whatever it may be. But I also think, AM hardware, or I'll call it the AM process in general, I think VELO3D has a really unique value add to this whole industry, and helping that continue in the future, I think, is integral for pushing the boundary of what we as people can design and achieve. So really enablement through more AM hardware and AM processes is vital.
Yeah, I don't usually take a vote in this, but I'll throw my hat in the ring too. I think the big place I'd like to see development is kind of in the education side. It seems that some designers take for granted the manufacturing solution before they start the design. The case studies where we've seen AM be extremely successful is where they just come in almost with an open book and push performance as far as they can, and then they find their manufacturing solution. I'd say they're in the minority, but the ones who do that, and they eventually meet Gene or somebody a lot like Gene, and then we print the part for them. Now they've just unlocked this whole new realm of speed, time to market, performance. Name your benefit. And Nick, as you mentioned, now they're getting parts that are high quality, fully dense, like any other machine part, but with geometries that are unachievable. So I just think that that frame, that mental model of when to think about your manufacturing solution, that's where that happens is probably the biggest difference I've seen.
Yeah, that's a good point.
Yeah, and that's kind of the time we've got for today. I would like to remind everybody, please follow VELO3D. We're doing these sessions about once every 2 weeks. We're a little flexible on time based on everyone's schedules, but look for us about every 2 weeks. Follow the channel, and you'll hear about the next one. And follow Purdue University, Zucrow Labs as well. Always fun to see what your team's up to. Any closing thoughts from the team?
Thank you guys for your support. We appreciate it.
Yeah, this has been good. Thanks for letting us come on and talk about our work.
All right. Thank you all for joining us today, and we'll wish you a happy Thursday. Till next time.